I want to look at some situations where we might need to multiply some probabilities. In this video, we're going to cover independent dependent events, conditional probabilities, as well as two-way frequency tables. So first of all, with independent events, these are going to be events in which the occurrence of one event does not affect the occurrence of the second event. They are independent of each other. So, for instance, if you flip a coin again, and flip a coin again, every single time that you flip a coin, it's independent of what happened before it. In other words, if I flip 10 heads in a row, on the 11th time, the probability of a coin landing heads again is still 1 out of 2. And how we calculate that probability of independent events is simply through multiplication. This is really just an extension of the basic counting principle. For instance, if we wanted to find the probability of getting 3 heads in a row, remember that calculating probability is a number of successful outcomes divided by the total number of possible outcomes. And in the numerator, when we think about our successful outcomes, well, we're going to toss a coin 3 times. And a successful outcome of getting 3 heads in a row means that we only have one option for success in the first toss, and that is getting a heads. And the same thing in the second and in the third time we flip the coin. But when we go down to our total number of possibilities, we are still flipping the coin 3 times. In the first flipping of the coin, there are 2 possible outcomes, heads or tails, and the same in the second and the same in the third. So 1 times 1 times 1 would be 1 out of 2 times 2 times 2, which is 8. Notice that for each of these, there's a probability of getting heads on the first one, and heads on the second one, and heads on the third flipping of the coin. So that total probability is just a half times a half times a half times a half. So let's say that we toss a coin and then roll a dice. What's the probability of the coin landing on heads and rolling a 3? So we're trying to find the probability of getting a heads and then a 3. Real simply, all we have to do is find the probability of getting a heads and multiply that by the probability of getting a 3. Well, our probability of getting a heads is 1 out of 2. And on our standard 6-sided dice, there's 1 3 out of the 6 different numbers. So our total probability would be 1/12. For dependent events, on the other hand, these are going to be events in which the occurrence of one event does affect the occurrence of the second event. To calculate these probabilities, again, it's going to be through multiplication, but the real important thing is to pay attention. Timing is really an important concept when we're talking about dependent and independent events, is because what happens first affects what happens next. We have to take that into account, like when you're taking cards out of a deck. Depending on what happened with the first card being taken out of the deck, there are now less cards in the deck. There may be less aces if that's what got dealt first, that sort of thing. So we always have to pay attention to that second event happening after the first one already occurred. A common type of problem that refers to this is a marble type of problem. Here we have a bag containing 12 red, 9 blue, 11 yellow, and 8 green marbles. We want to find the probability that a red and then a blue marble are drawn. So we want to find the probability of red and then blue. So because we see that and, we're going to want to multiply. Finding our probability of the red, there are 12 reds. And we're going to have to add up how many marbles there are in total. So when we add 12 plus 9 and 11 and 8, we'll get 40. Now when we multiply by the probability of getting a blue, there are 9 blue marbles in the bag. However, we just took one of the red marbles out. So there are less marbles in the bag in total. In fact, instead of 40, now there's 39. So we go ahead and do a little simplifying. 4 goes into each of them. 3 goes into 39 13 times. So we multiply and we'll get 9 out of 130. Let's try another one. What's the probability of drawing 2 red marbles in a row? So that means we want to find the probability of getting a red and then another red. So we think about each of those events happening one right after the other. First of all, getting a red marble out of there. Well, there are 12 red marbles in the bag out of the 40 total. So we imagine that we went in the bag and we were able to pull a red one out. Now when we're going to multiply by the probability of getting that second red, since we've taken a red marble out, now there are less red marbles in there, as well as less marbles in total. So we're going to multiply by 11 over 39. Going through that simplifying process again, 4 goes into each of those. 3 goes in there 13 times. And so we end up with 11 out of 130. A very common distinction that happens with this type of problem on ACTs, SATs, MCAs, all of that, is this idea of replacement. Here we have the same problem, the same bag with the same number of marbles in it. We're still going to continue to draw 2 marbles out, one right after each other. It's just that this time, after we take the first marble out, we check on what color it is, and then we put it back in the bag before we draw the second marble. In that case, here, let's find the probability that we get a red and then a blue again. So once again, red and then blue. Right. Probability of getting a red, there are 12 of them out of the 40. But we're going to take that one marble out, recognize that it's red, and put it back in the bag. Because we put it back in the bag, now that probability of getting a blue is not affected by what happened the first time around, because there are 9 blue marbles in there, but we put that one marble back, so we're back to having 40 total marbles in the bag. Now we go through and simplify again. 3 out of 10, there's no other canceling that's going to happen, so we'll end up with 27 out of 400. So when we have that replacement, these 2 events are no longer dependent on each other, and it goes back to being 2 independent events. So if we want to find the probability of getting a red and then another red, we'll find the probability of getting a red the first time, 12 out of 40. We checked on the marble, saw that it's red, put it back in the bag, and go for another red one. And there are 12 marbles in the bag again out of the entire 40 that are still there. So cancel again, 3 out of 10, 3 out of 10. That looks like 9 out of 100. A conditional probability is going to be the probability that an event will happen given that another event has already occurred. So it's really like the second part of those dependent probabilities. But I want to point out notationally what that looks like. That when we see a probability written like this, where we have the B and the vertical line and an A, it's that vertical line right there means B given that A has already happened. In a lot of ways, we can just kind of reason our way around it, but there are going to be some other situations where we can't, and we're going to need to rely on this formula that we have here, that to calculate that probability, we will find the probability of A happening and then B happening, and divide that by the probability of just A happening. In this case, the marble problem is kind of a trivial example, but let's say we still have 12 red, 9 blue, 11 yellow, and 8 green marbles. We're going to draw 3 of them, and what's the probability that the second one will be blue after a red one has already been drawn? And of course, we're going to assume that there's no replacement happening in this one. Well, we already know how to do this problem, which makes it kind of trivial. That what we're trying to find is the probability of getting a blue one after a red one has already happened. And we can just think about that. Let's assume that we've gone in and already gotten a red one out of there. And now we want to check on the probability of the blue one. Well, there would be 9 blues in the sack of marbles. But because we've already taken a red one out, there are only going to be 39 marbles in there instead of the 40 total. When we simplify that, we'll get 3 out of 13. How would this look if we used that formula, which said that the probability of B happening after R would be the probability of blue and red divided by the probability of the red. Right? So just to get used to using this formula, we would find that probability of getting a blue, which would be 9 out of the 40. Multiply that by the probability of getting a red, 12 out of the 39, because there's one less in there, divided by the probability of just getting a red, 12 out of 40. When we simplify all of this, we can do a little canceling at first. 9 goes in there, and they each go 3 times, so 3 times 3 and 3 times 13. 4 goes into both of these, so 10 and 3, which means we'll have 9 out of 130 divided by 12 out of 40. So we multiply by the reciprocal. And do a little more canceling. 4 goes into both of these. 3 goes in there. 10 goes in there. And looks like we're left with our answer of 3 out of 13. The same probability. One that's an example that's a little less trivial here is that a restaurant, digs through its receipts and keeps track of its data and finds out that 25% of its customers order chili and 4% of them order chili as well as a baked potato. We want to find the probability that a customer who orders chili is also going to order a baked potato. So we think about that as like, the waiter or waitress comes and asks for the order, and the person says, I will take a bowl of chili, and now we want to find the probability. What's the next thing they're going to say is going to be baked potato. So we want to look at the probability of getting a potato, given that they've already said they're going to order chili. To calculate that probability, we find the probability of both of them, both ordering a potato and chili, which was 4%. And divide that by the probability of just ordering chili, the 25%. And now simplify to 4 out of 25, or about 16%. Oftentimes, the way that standardized tests are going, like ACTs, SATs, and MCAs, the way that they're going to represent conditional probabilities is through a two-way frequency table. For instance, in this table, we got the demographic breakdown of a certain high school. So we could see how many students are male and female in each of the grades. So we can see that there are 155 ninth graders who are male and 180 ninth graders are female, and so on. Now, if we want to find the probability that a student is male, given that they're 12th grade, using the formula, we would find the probability of male and 12th grade divided by the probability of being in 12th grade. So we look to our table. We can see that for the people who are male and in 12th grade, that's this 160 number. So there are 160 of the students, out of all the students. And I went ahead and added them all up, and there's 1,350 students in the entire school. Now we need to take that probability and divide it by the probability that a student is in 12th grade. So in 12th grade, these are all the students that are in 12th grade. And if we add all of them up, that's going to be 330 people. So that would be 330 out of this 1,350 students. Of course, going through the canceling, our denominators will cancel. We'll have 160 out of 330, which is 16 out of 33. One thing I notice in more of these problems that I do is those denominators are always going to cancel. And so there's a real slick way to kind of go about doing these where it doesn't have to be as messy. For instance, if we want to find the probability that students in 10th grade, given that they're female, instead of focusing on the probabilities of these things happening, since we have our two-way frequency table, we can really just focus on the number of ways that these things can happen. So we want to think about the number of ways that a student can be in 10th grade and a female. And 10th grade females is right here, 135. Out of, not the entire student body, but out of the females. So because it's given that we are talking only about females. So that would be all of these people. When we add that up, the 180 plus 135 plus 190 plus 170 is 675. Then when we go ahead and simplify that, we'll end up with just 1/5. I want to point out one more thing, that order matters. When we're talking about the probability that a student is in 10th grade given that they're female, that was 1/5. But what about the probability that a person is female given that they're in 10th grade? So we want to go and look at the females that are in 10th grade again, that same 135 right here. But this time, instead of dividing it by the total number of females, we want to divide it by the total number of 10th graders. So all of these people. And when we add that up, we should get 310. So depending on what group we're taking it out of, that gives us a different denominator. Simplifying, we'll end up with 27 out of 62, which is closer to a half than it is to a fifth.